So just going through the review, the practice test for the Unit 2 test. Which of the following is the formula to determine the mean of a probability distribution? All right, so that would be choice C. All right. This is the mean of binomial distribution. This one is the standard deviation of binomial distribution. This one really isn't anything. So, just in case. What are the four conditions necessary for a distribution to be considered binomial? Fixed number of trials, fixed probability, independent events, two outcomes. All right, number 3, suppose a coin is flipped and a color is selected from the following set: black, white, red, orange, and purple. We can use abbreviations, but it's list of sample space. I would also allow for a tree diagram, because that's the same as creating a list of all possible outcomes, which is what a sample space is. So you can go either way with it. But if we do it with just a sample space, it would be, well, we have the coin, then we have the color. So we could say HB, HW, HR, HO, HP. We could say, so now tails, TB, TW, TR, TO, and TP. All right. Or you don't have to do both of these methods, but you could also do it as a tree diagram. So heads, tails, and 4 branches for each one. 5. 5 branches for each one. So black, white, red, orange, purple, and then just do the same thing for tails. So if you want to do tree diagram or sample space, either would be acceptable. Number 4, 3 geometric figures are selected from the sample space below without replacement. What's the probability of the first one selected as a lightning bolt? All right, we'll start with that. So lightning bolt. All right, so I got one of those out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the remaining 2 are not triangles. So not triangles. All right. So the lightning bolt's out of the picture. We're looking for things that are not triangles. So I'll use a highlighter here. This one, 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 and this one. All fair game. So if I select one at random, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 possibilities out of the 11 shapes that are available, because remember the lightning bolt's gone. All right, so 9 out of 11. And then if I select another one, well, one of the non-triangles is gone. All right, so I'm down to 8, and there are 10 geometric figures left over. All right, so that's going to be, we just run the numbers, so 9 times 8. You don't need the 1. 12 times 11 times 10. Multiply across the top, across the bottom. So you could say 72 over 1320. You can do 3 over 55, or you can do 0.0545. All right. Number 5, probability of self-taught given that the individual was a male. So this is my male row. So probability, self-taught, given male. Here's my self-taught individuals, so 19, and here's the total number of males, so 58. And again, you can pop that in the calculator, see what comes out of it. Represent your answer as a fraction, which I've done, or a decimal of 3 significant digits, so 0.328. According to Gallup poll, 60% of American adults prefer saving over spending. A simple random sample of 50 adults was polled on whether they preferred saving over spending. What is the probability that at most, I should get the at in there, at most 20 adults prefer saving, I would assume over spending, right? So this is actually a binomial situation. We have fixed number of trials, fixed probability, independent events, 2 outcomes. So I'm just gonna grab these real quick. Oops, sorry, I hit the wrong thing. This is not something that you would need to write for this question. I just want to be able to point to it. Fixed number of trials, we have a simple random sample of 50 individuals. All right, fixed probability. That's the 60%. There's no indication that that's changing. Independent events. All right, so 2 possibilities, saving or spending. Apologies, I meant that for the 2 outcomes. But also, we'd have to make the assumption, so I'll say assumed, that they're independent events. Right? And that's because we don't know what the interaction is between saving and spending. You know, if my friend is a saver, does that make me more likely or less likely to be a saver? I don't have the answer to that, so we just assume that they're independent. All right. So I want the probability that x is less than or equal to 20. Because it's binomial, I'll use the binom CDF. So that's in my toolbox. So let's say you're starting right from the beginning of the toolbox, go to probability, distributions, binomial, and you'll see the one with the less than or equal, binom CDF. 20 is my quote-unquote M value. Number of trials is 50, probability of success is 0.6. So 20, 50, 0.6. So we're looking at about 0.00336. All right, again, you don't have to write this. I just did that to indicate how I knew that I would use binom CDF. All right, similar question, or at least framework. Simple random sample of 50 American adults are polled as to whether or not they prefer saving over spending. So they're asking for the expected value. So for A, mu is equal to NP. And again, I know to use this formula because it's a binomial distribution, which we talked about in the previous question. So 50 times 0.6 is going to be 30. For B, determine the standard deviation of Americans that prefer saving over spending. So sigma is equal to the square root of NP times 1 minus P. So the square root of 50.6 times 1 minus 0.6. So square root of 50 times 0.6 times 1 minus 0.6. All right, so we're talking about 3.464. 3.464. Determine the usual interval based on your answers to parts A and B, correct to 3 significant digits. So that's mu plus or minus 2 sigma. All right. So that's 30 plus or minus 2 times 3.464, approximately. 30 minus 2 times 3.464, and then 30 plus. So 23.072, going on up to 36.928. And I said, would it be unusual if only 10 Americans preferred saving over spending? Yes. Yes. 10 is not in the usual interval. All right, and this is my usual interval here. So it doesn't fall in that interval, so it would not be considered usual, which would make it unusual. So looking at number 8, says Professor Can hit the bullseye on a dartboard approximately 12% of the time. One day he decides to throw a dart as many times as it would take to hit the bullseye. What is the probability he misses 14 times before hitting the bullseye? Okay, so you could use the geometric distribution function in the calculator if you want, or you could just do simple multiplication. So I'll do it both ways. So if you miss 14 of them, so this is the probability of making it. So probability of hit is 0.12. Probability of miss is 0.88. So miss 14 times would be 0.88 raised to the 14th power times make or hit once. So that would be times 0.12. So I could do 0.88, not squared, raised to the 14th power times 0.12, close it up, and we're looking at something that would round to 0.0200. All right. Now you could also do it with, if you go into probability, so I'll take you back to the beginning, toolbox, probability, distributions, go to the one that says geometric. We would select Geom PDF. All right. And then this would be the instance in which you get your first make and the probability of getting a make or a hit. I keep saying make. 15.12, lock it in, you get the same thing. All right. So you don't have to do it both ways, one way or the other. If this makes sense to you, then you really don't even need to look at this, but maybe you like this method better. It's up to you. All right. Number 9, on average, Professor Can completes 4 Monday New York Times crossword puzzles during any given hour. During a 2-hour period, Professor Can attempts to complete as many Monday puzzles as possible. What is the probability he can complete 10 Monday puzzles in the course of a 2-hour period? All right. So, and then show the functions that were used in your calculator to arrive at the answer. All right. So we're looking at, I remember in the notes, mu. We use mu. Calculator uses lambda. It really doesn't make a difference. But what we would say is that over a 2-hour period, the mean mu should be equal to, I'll normally do 4 during any given hour. All right, so that means that I should be able to do 8 in a 2-hour period. So for this, I could just jump right to the Poisson distribution. All right, and it's really the same setup. If I do Poisson PDF, number of successes that I intend to have versus what I expect to have. All right, I'd like to think I could do 10, but if I'm averaging 8, then it's a little bit different from what I'm averaging, so it shouldn't be a very, the highest probability, but oops. Right, so we're looking at something like a 10% probability, roughly. So 0.0993. Right, the closer I am to my actual average, so if I'm averaging 8 per 2-hour period or 4 per hour, the closer I am to that, the higher the probability would be. But the further I move away from that, the lower the probability would be. Right. So then number 10, a local business has advertised that they are hiring. There are 12 candidates for the insurance positions and 15 candidates for the legal positions. If the business will only hire 10 of the candidates, what's the probability that 5 insurance candidates and 5 legal candidates will be hired? All right, so we basically itemize it. It's not anything much more complicated than that. So we have what are we doing first here? Insurance, then legal, and then whatever the total is. So from the insurance candidates, 12 candidates for insurance, they're going to take 5 of them. So 12 C5, combination of 12, 5. All right. So that's my insurance. For the legal, we have 15 candidates, and they're going to take 5. So 15, 5. And overall, we have 27 candidates. So this is all. And they're hiring 10. So run this through your calculator and you'll have it. Right, so we're going to go into the toolbox. All right, so toolbox, let's get back out of here. We'll go to combinatorics. I really want to just kind of manufacture this in my calculator. And by the way, I'll preface this by saying I'm not really going to bother with the hypergeometric function on this because it's so convoluted in terms of where you have to put the numbers that it's almost, I would say it's probably the least helpful of all the built-in functions related to this topic. So I'm just going to do it this way. All right, so we're going to create a couple of combinations and then put it over another combination and then just run through with the 12, the 5, the 15, the 5, and the 27, and the 10. And again, well, I didn't say it in this video, but this number is the sum of these two values. All right, just like this number is the sum of these two values. So once you have the top, you pretty much have the bottom too. All right, so we're looking at about 0.282, something in that neighborhood. All right, and so that's all she wrote.